The interstellar traveller 3I-ATLAS just did something no one predicted. As it swept through perihelion on October 29, 2025, it suddenly brightened and shifted to a colour bluer than the Sun itself. That's not speculation. That's what Avi Loeb just confirmed using new data from Stereo, SOHO and GOES spacecraft. And here's the unsettling part. Loeb's team admits they can't explain it. And when Avi Loeb says unclear, that's not routine. The scientific community is divided. Some see a super volatile interstellar comet reacting violently to the Sun's energy. Others suspect something far stranger, a fragment of engineered material awakening only under extreme radiation. Whatever the truth is, one thing is certain. 3I-ATLAS has just outshone expectations, literally. Stay with me until the end, because tonight we go through these recent findings with a fine comb, and by the end you will realise why no one is ready for what comes next. Because as 3I-ATLAS returns to view on December 19th this time, it may not just be a visitor from another star. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think of this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Breaking news. Hidden behind the Sun, yet glowing bluer than the Sun itself. October 29th, 2025 marked perihelion for 3I-ATLAS, the third confirmed interstellar object to visit our solar system. You'd think that would be the story. You'd think we'd be celebrating another cosmic tourist making its closest pass to our star before vanishing back into the void. But what happened instead has professional astronomers checking their instruments, rechecking their calibrations, and quietly asking each other if what they're seeing is even possible. Multiple spacecraft coronagraphs captured something unprecedented. Stereo A's heliospheric imager and coronal camera, SOHO's LASCO C3 instrument, and GOES 19's CCOR-1 weather satellite all reported the same impossible thing. The object brightened, not gradually, not predictably. It exploded in luminosity with a scaling law that defies every comfortable model we have for cometary behaviour. The numbers tell a story that shouldn't exist. Brightness increased with heliocentric distance to the power of negative 7.5, give or take 1. Let me put that in perspective for you. Most comets brighten as they approach the Sun, sure, following a gentle power law around negative 3 to negative 5. That's physics we understand. Ices sublimate, dust reflects sunlight, the envelope grows. But negative 7.5? That's not a comet warming up, that's something else entirely. Orders of magnitude steeper than anything in our databases of normal cometary visitors. Think of it like this. You're driving toward a destination. As you get closer, you press the accelerator. Normal comet behaviour is like smoothly increasing speed. You go from 50 to 60, 60 to 70. Predictable. Linear acceleration. What 3I-ATLAS did near perihelion is like flooring the accelerator and watching your speedometer jump from 50 to 500 in seconds. The vehicle doesn't respond that way. It can't, unless something fundamental about the vehicle is different, and then there's the colour. GOES 19's CCOR-1 coronagraph recorded not just brightness but hue, and the photometry came back bluer than the solar spectrum itself. Not slightly blue, not ambiguously blue, definitively, measurably bluer than the star it was orbiting. Coronagraph colour indices don't lie easily across multiple independent instruments. When Stereo A, SOHO, and GOES all converge on similar observations, you're looking at something real, not an artifact of one sensor's quirks. The luminous envelope stretched roughly 300,000 kilometres across. That's about 25 times Earth's diameter. Imagine wrapping our entire planet in a glowing shell and then stacking 24 more Earths side by side within that glow. That's the scale of what GOES 19 observed. And it wasn't just reflected sunlight creating that envelope. The object appeared to be emitting light, radiating its own visible signature in wavelengths that shouldn't dominate if this was simple dust scattering. Here's where it gets stranger. 3I-ATLAS was hidden from Earth during this display. Solar conjunction meant that from our perspective on the ground, the object was lost in the Sun's glare, invisible to every telescope pointed skyward from the surface. But spacecraft don't have that problem. Coronagraphs are designed to block the sun's overwhelming disk and image the faint corona beyond. They can see what Earth cannot. On October 29th, while we were blind, our robotic eyes watched something unfold that no human observer could witness directly. The instruments had a front row seat to an event we're only now beginning to process. Avi Loeb and his collaborators reported these findings in recent preprints and posts, citing the verified instrument data. The paper is cautious in its language, as it should be. But buried in the technical prose is a sentence that should make anyone pause. The reason for 3I-ATLAS' rapid brightening, which far exceeds the brightening rate of most Oort cloud comets at similar distances from the Sun, remains unclear. When career astronomers write that something remains unclear, they're not being coy. They're admitting that their models don't work. The physics they trust is insufficient. This isn't peer-reviewed yet. That matters. Extraordinary claims demand extraordinary evidence, and the process of verification is still underway. Instrument teams will scrutinize calibrations. Independent analysts will request raw data frames. Someone will find an error, or someone will confirm the trend. Either outcome changes what happens next. But right now, in this moment, we have multiple spacecraft telling us the same improbable story, and no one has a comfortable explanation. If this holds up, we're not just rethinking one comet. We're rethinking what comets can be. We're questioning volatile chemistry we thought we understood. We're entertaining possibilities that sounded like science fiction yesterday. Some of those possibilities involve exotic natural processes we've never observed at this intensity. Others involve materials that don't form in nature at all. I'm going to walk you through what the instruments actually saw, why bluer matters, what brightness laws mean, and why professional scientists are unsettled. We'll examine the data, the rival explanations, the calibration risks, and yes, the wildest what-ifs. By the end of this first act, you'll know exactly what was reported and why it's causing quiet alarm in observatories around the world. October 29th, 2025. Perihelion. Mark that date. What happened behind the Sun might be the beginning of a story that rewrites the rules, or it might be a cautionary tale about rushing to conclusions. Either way, 3I-ATLAS just did something no one predicted, and we have 5 weeks until it re-emerges into Earth's view. 5 weeks to prepare for whatever comes next. The countdown starts now. Part 2, Instrument Deep Dive, Coronagraph Observations. 3 spacecraft, 3 independent sensor systems, 3 confirmations of the same impossible observation. Stereo, A, carries 2 instruments relevant to our story. The heliospheric imager, called HI-1, captures broad, faint fields far from the Sun, tracking structures in the solar wind and occasionally catching comets passing through its view. The coronal camera, COR-2, zooms closer to the solar limb, imaging the inner corona where the Sun's atmosphere transitions into interplanetary space. Both instruments work by blocking the Sun's direct light, letting them see objects that would otherwise drown in solar glare. Think of it like shading your eyes with your hand to spot a faint firefly hovering next to a spotlight. The spotlight doesn't disappear, but you can finally see the firefly. SOHO's LASCO. C3 instrument has been observing the solar corona since 1996. It's a veteran. Wide field of view, less frequent image cadence than modern sensors, but absolutely reliable. Decades of calibration data, known quirks. When LASCO C3 reports an unusual brightness, teams know how to cross-check against its historical behaviour. This isn't a new instrument making rookie mistakes. GOES. 19 is a weather satellite. Its CCOR-1 coronagraph was designed to monitor solar eruptions for space weather forecasting, not to chase interstellar comets. High cadence, low noise, excellent temporal resolution. When GOES 19 captures something, it captures it frame by frame with the kind of consistency that makes artifacts easy to spot. Anomalies that persist across hundreds of sequential frames are rarely instrumental flukes. Why do spacecraft coronagraphs see objects behind the Sun when ground telescopes can't? Geometry. From Earth, 3I-ATLAS was hidden by the Sun's disk during solar conjunction. Line of sight blocked. Game over for terrestrial observers, but spacecraft orbit in different positions. Stereo. Sits at a Lagrange point that gives it a side-angle view. SOHO orbits the Sun-Earth L1 point with a slight offset. GOES 19 hovers in geostationary orbit, but its coronagraph looks outward, catching objects in angular positions where the Sun's glare can be mechanically blocked. They weren't trying to observe 3I-ATLAS. They just happened to be looking at the right patch of sky when something extraordinary occurred. Observation windows matter. Perihelion occurred on October 29th, but the instruments didn't all capture data simultaneously. Stereo A's HER says one picks up motion over days, building sequences that show trajectory and brightness evolution. Core 2 provides closer snapshots when the object crosses its field. LASCO's C3 has wider but intermittent coverage, grabbing frames every few hours depending on telemetry schedules. JWST delivered high-cadence monitoring frame after frame, building a continuous record through the critical hours around closest approach to the Sun. The 300,000-kilometre luminous envelope came from JWST's CCOR-1 data. Observers measured the apparent angular size of the glowing region around 3I-ATLAS and converted it to linear kilometres using the object's known distance from the spacecraft. 300,000 kilometres, not a typo, not a misplaced decimal. That's the scale of the extended coma captured in multiple frames. Comets have comas, we expect that. But the size and brightness of this envelope, coupled with its colour properties, pushed the observation into uncharted territory. Colour photometry is where things get technical but crucial. Coronagraphs don't just record brightness, they use filters to sample different wavelengths, building a rough spectrum from the ratios of light in each filter band. Solar light has a known spectrum, peak in the yellow, balanced across the visible range. When you divide an object's filter ratios by the Sun's filter ratios, you get a colour index. Positive means redder than the Sun, negative means bluer. The measured colour index for 3I-ATLAS during perihelion placed it firmly in the blue, not marginally, not ambiguously. More short wavelength light relative to long wavelength than the Sun itself produces. Calibration is never perfect. Stray light can scatter inside the instrument, contaminating measurements. Vignetting affects how evenly the detector responds across its field of view. Instrument response curves vary with wavelength in ways that require careful correction. Background subtraction is an art as much as a science, especially when you're trying to extract a faint moving object from the bright coronal background. Any of these could introduce error. Any of these could make a neutral spectrum look artificially blue. But here's the thing. All three independent instruments reported consistent trends. Stereo A, SOHO, JWST. Different designs, different calibration histories, different teams. When multiple sensors converge on the same anomaly, the artifact hypothesis gets weaker. Not impossible, just less likely. You'd need a conspiracy of errors, all biased in the same direction, affecting different hardware in the same way. Possible, yes. Probable? That's where the debate begins. Raw coronagraph frames look like grainy black and white images with the Sun's disk masked out by a circular occulter. Processed frames add false colour to highlight brightness differences and subtract background models to isolate moving objects. When you plot brightness over time and overlay the data points from different instruments, you see the curve. The steep, alarming curve that shouldn't exist for a normal comet. Typical comets brighten with a power law exponent around 4. Some go as steep as 5. We have theories for those. Dust production ramps up. Surface area increases as fresh ice is exposed. Volatile sublimation accelerates. But 7.5, that's not a ramp, that's a cliff. If brightness normally doubles every 0.1 astronomical units of approach, this object's brightness jumped by tens to hundreds of times faster in the same distance interval. The math doesn't lie. The physics we know doesn't produce that curve. Brightness alone doesn't tell the whole story. You can make something look brighter by reflecting more sunlight, or by emitting your own light. Reflection depends on surface area and albedo. Emission depends on temperature and material properties. The colour gives you the clue. Blue emission in a cometary context isn't impossible, but it's unusual, and the intensity observed here exceeds what simple gas fluorescence should produce at these distances. So what exactly produced that blue light? That's the question hanging over every observatory that plans to observe 3I-ATLAS when it re-emerges, and every answer being proposed right now comes with caveats, uncertainties, and assumptions that make professional astronomers uncomfortable. We're about to pull apart the brightness curve piece by piece and see if the numbers really support the extraordinary claim, or if there's a simpler, less dramatic explanation hiding in the details. Part 3. Photometry and Brightness Curve Analysis. Brightness scales with heliocentric distance raised to the power of negative 7.5 plus or minus 1. Let me unpack that sentence because it's the core of why astronomers are nervous. Heliocentric distance means how far the object is from the Sun, measured in astronomical units. 1 AU is Earth's average distance from the Sun, roughly 150 million kilometres. As a comet approaches the Sun, heliocentric distance decreases. As it recedes, distance increases. Photometry measures brightness, usually in magnitudes or flux units. The scaling law tells you how brightness changes with distance. For a normal comet, brightness increases modestly as it approaches. You might see a power law exponent of -3. That means brightness triples when distance halves. -4 means brightness goes up by a factor of 16 when distance halves. These are the gentle curves we're used to, the ones that match sublimation physics and dust production models. -7.5 means brightness increases by a factor of 180 when distance halves. That's not gentle. That's explosive. Building the brightness curve requires data from multiple sources. Pre-perihelion observations came from ground-based telescopes tracking 3I-ATLAS as it approached. Those gave the baseline. Then spacecraft coronagraphs picked up the object during solar conjunction, providing the critical perihelion data points. Analysts plotted logarithm of flux against logarithm of heliocentric distance, fit a line to the points, and extracted the slope. That slope is the exponent, -7.5. Error bars matter. Not every data point is equally reliable. Some frames had higher noise, some were affected by stray light or cosmic ray hits. Some had uncertain background subtraction. When you fit a line through noisy data, you get confidence intervals. The plus or minus 1 on the exponent reflects that uncertainty. The real value could be as shallow as -6.5 or as steep as -8.5. Either way, it's far outside the normal range. Multiple instruments tying to a similar slope strengthens the claim. If only stereo A had reported -7.5, you'd suspect an instrument-specific problem. If SOHO had reported -4 and GOES had reported -9, you'd conclude the data were inconsistent and unreliable. But when independent sensors converge on similar steep slopes, the signal becomes harder to dismiss. Something real is happening. The question is whether that something is in the object or in the measurements. Comparison with canonical comets makes the anomaly stark. Typical Oort cloud comets follow power laws between -3 and -5. Halley-type comets, Jupiter family comets, long-period comets, they all cluster in that range. A few comets have shown steeper brightening during outbursts or fragmentation events, but those are transient spikes, not sustained trends. 3I-ATLAS maintained its steep slope across multiple days and multiple instruments. That's not an outburst. That's sustained behaviour demanding an explanation. Time evolution adds another layer. Early tracking data showed more modest brightening, consistent with a power law around -2 or -3. Then, within days to hours of perihelion, the slope steepened dramatically. The transition wasn't gradual, it was abrupt. One moment the object was behaving like a normal if somewhat active comet. The next moment it was something else. If the exact timing is uncertain in the current data, we at least know the steepening occurred in the final approach, compressed into a narrow window around closest solar distance. Plausible mechanisms for steep brightening exist in theory. Pressure-cooked volatile release is one. Imagine a comet with a thick insulating crust that suddenly cracks under thermal stress, exposing volatile-rich material underneath. The sudden exposure triggers rapid sublimation, flooding the coma with gas and dust, spiking brightness. Explosive fragmentation is another. A comet nucleus fracturing into pieces increases surface area instantly, releasing trapped volatiles and producing a brightness surge. Fluorescence transitions in certain molecules can amplify emission if solar UV pumps atoms into excited states that then radiate visible light efficiently. But here's the problem. Pressure-cooked, release, and fragmentation produce brightness spikes that fade quickly. Hours to days, not sustained steep slopes, across multiple days. Fluorescence depends on specific molecular species being present in huge quantities in specific UV flux conditions. You need just the right chemistry and just the right distance from the Sun. Possible, yes. Likely for an interstellar visitor with unknown composition? That's the gamble. Alternative non-physical explanations must be considered. data artifacts are always possible. Saturation effects occur when a detector's pixels max out, clipping the signal and making brightness measurements unreliable. Background subtraction errors happen when you misestimate the brightness of the surrounding corona and accidentally subtract too little or too much from the object's signal, artificially inflating or deflating the measurement. Cosmic ray hits can mimic point sources, though those usually appear in single frames and don't persist across time sequences. Investigators have to rule out these alternatives systematically. They examine raw frames for saturation. They check temporal coherence to see if brightness tracks smoothly or jumps erratically. They compare different instruments' backgrounds and verify that subtraction methods are consistent. It's painstaking work. It takes time. Until that work is complete and published, every number carries an asterisk. The luminous envelope data provides a cross-check. Extended size versus brightness trades off in a predictable way. If brightness increased purely because the coma scattered more sunlight, you'd expect the envelope to grow in size proportionally. Surface brightness per pixel stays roughly constant. But if brightness increased because the object started emitting light rather than just reflecting it, surface brightness per pixel can increase even if the envelope size stays the same or grows more slowly. The GUS 19 observation suggests emission, not just reflection, because the envelope's surface brightness was too high for pure scattering. Numbers don't lie, but numbers can be misread. Decimal places can shift. Units can be misapplied. Calibration constants can be outdated. Every astronomer knows stories of dramatic discoveries that evaporated under scrutiny. Some turned out to be instrument glitches. Some were mathematical errors. Some were real signals misinterpreted. The history of astronomy is littered with cautionary tales about jumping to conclusions before the data are fully vetted. That's why what happens next matters so much. Independent teams will reanalyze the same data. They'll request access to raw frames. They'll run their own photometry pipelines. They'll compare notes. And in a few weeks, maybe a few months, a consensus will emerge. Either the steep slope is real, and we need new physics to explain it, or the steep slope is an artifact and we need better calibration. Right now, we're in the liminal space between discovery and confirmation, where every assumption is provisional and every claim comes with a disclaimer. But the colour is harder to dismiss. And that's where we turn next, because bluer than the sun means something specific, something that can't be waved away with background subtraction or saturation excuses. Colour is a ratio. It's self-calibrating in ways that absolute brightness isn't. When three independent instruments all measure blue, you're looking at a real spectral signature. And spectral signatures tell you about physical processes, about what's glowing and why. That's the key to unlocking this mystery. Part 4. Colour shift. Bluer than the sun. Bluer than the sun. 3 words that shouldn't describe a comet. The sun's visible spectrum peaks in the yellow, around 570 nanometers, with a smooth distribution across shorter and longer wavelengths. We call it white light, but it's really a blend. When you disperse sunlight through a prism, you get the familiar rainbow, and the sun's brightness curve shows that yellow-green dominates. Objects that reflect sunlight should, ideally, have spectra that match the sun. Neutral colour, grey dust, white ice. That's the default. Blue means relatively more emission at shorter visible wavelengths, more violet, more deep blue, less yellow, less red. For an object to measure bluer than the sun, its spectrum must be weighted toward the short wavelength end compared to the solar reference, and that weighting requires a mechanism. Either you're scattering light in a way that favours blue, or you're emitting light in a way that produces blue, or both. Chronograph colour photometry works by taking images through different filters. One filter passes blue light, say around 450 nanometers. Another passes red light, say around 650 nanometers. You measure the brightness in each filter, take the ratio, and compare that ratio to the sun's ratio in the same filters. If the object's blue to red ratio is higher than the sun's, the object is bluer. If lower, redder. Simple in principle. Tricky in practice because filters have finite widths, detectors have wavelength-dependent sensitivities, and backgrounds vary across the field of view. The observed deviation in 3I-ATLAS's case wasn't marginal. It wasn't a 1 sigma flicker, it was a clear multi-sigma shift. Measured colour indices placed the object definitively on the blue side of the solar spectrum, and critically multiple instruments agreed. Stereo A, SOHO, goes 19. Different filter sets, different calibration pipelines, same conclusion. That convergence is hard to explain if the blue is just an artifact. Possible physical origins for blue emission in a cometary context fall into three broad categories. First, gas emission lines or molecular bands. Certain molecules emit strongly at specific wavelengths when excited by solar UV. Cyanogen, CN, emits around 380 nanometers in the near UV to violet. Diatomic carbon, C2, has bands in the blue and green. These emissions can give comets a greenish or bluish tint when those molecules dominate the coma. It's common for comets to look slightly green in images because of C2 and CN emission. But 3I-ATLAS's blue is reported to be more intense and spread across a wider envelope than typical cometary green. Second mechanism is scattering off small submicron dust. Rayleigh scattering, the same physics that makes Earth's sky blue, favours shorter wavelengths. If the dust particles in 3I-ATLAS's coma are very small, smaller than the wavelength of visible light, they'll scatter blue light more efficiently than red. You'd see a blue-tinted coma even though the dust itself might be dark or neutral in bulk. The catch is that Rayleigh scattering requires specific grain sizes and a lot of small particles. Cometary dust is usually too large for strong Rayleigh effects, which is why most comet comas are neutral, or slightly reddish, not blue. Third mechanism is plasma processes. Electron impact excitation happens when high-energy electrons collide with atoms or molecules, pumping them into excited states that then emit visible light. Solar wind electrons could drive this near the Sun. Certain emission lines, like oxygen forbidden lines around 500 nanometers, or hydrogen Balmer lines, could contribute to visible blue or blue-green emission. Plasma fluorescence in a dense coma under intense solar UV might produce blue light, if the right ions and excitation conditions exist. Known cometary emissions include CN and C2, as mentioned, which create the classic green comet colour. But 3I-ATLAS differs. Magnitude matters. If CN and C2 alone were responsible, you'd need enormous production rates to explain the brightness. And the spatial extent of the blue envelope suggests something more widespread than concentrated molecular bands. The GOES observation showed the blue colour persisting across a 300,000 kilometre envelope. That's huge. CN emission typically dominates in the inner coma, within 10,000 to 50,000 kilometres of the nucleus. Extending blue emission to 300,000 kilometres requires either a massive production rate or a different emission mechanism. Emission versus reflection becomes the critical question. Sunlight reflected by dust produces a spectrum that mirrors the sun's. Neutral colour. An object emitting its own light produces a spectrum determined by the emission mechanism. Atomic emission lines, molecular fluorescence, thermal radiation. Each has a characteristic shape. The Gauss coronagraph observation suggests emission because the brightness and colour don't scale the way pure reflection would. Reflected light should dim rapidly as the envelope expands, conserving total luminosity. Emitted light can maintain brightness if the emission process is energized continuously by solar flux. Supervolatiles offer a potential connection. Carbon monoxide, CO, and carbon dioxide, CO2, have emission features and fluorescence channels. Spherex reportedly detected CO2 in 3I-ATLAS's spectrum back in August, well before perihelion. That detection established the object as volatile rich. CO2 ice sublimates around 150 Kelvin, colder than water ice. If 3I-ATLAS carried substantial CO2, it could be outgassing vigorously near the Sun, populating the coma with molecules that then fluoresce under UV excitation. Some CO2 emission bands fall in the blue to UV range. A massive CO2-driven coma could, in theory, produce extended blue emission. But caution is required. Instrument calibration and scattered sunlight can mimic bluer measurements, even when the object's true spectrum is neutral. Coronagraphs are optimized for observing the corona, not faint-moving objects. Colour indices derived from coronagraph data carry larger uncertainties than indices from dedicated photometric instruments. Stray light scattered inside the instrument might preferentially affect one filter over another, biasing the colour ratio. Vignetting could make the blue filter more sensitive near the field centre, where the object happened to be, artificially enhancing the blue signal. Yet corroboration across multiple sensors reduces the chance of purely instrumental artifact. If Stereo A's blue measurement were just stray light, why did SOHO and GOES also measure blue? If it were vignetting, why did it persist across multiple frames as the object moved through the field? Artifact explanations have to account for consistency. Single instrument anomalies are easy. Multi-instrument consistency is hard. The paper's own words are telling. Quote, "The reason remains unclear." End quote. Career astronomers don't write that lightly. They write it when their models don't fit, when the obvious explanations fail, when the data point somewhere uncomfortable. Avi Loeb has built a reputation around pushing boundaries and asking uncomfortable questions. His team's candour about not having an answer is both honest and unsettling. It leaves the door open. Open for exotic natural chemistry. Open for instrument misreads. Open for something stranger. Whatever produced that blue light, the pattern points to processes operating at scales and intensities we don't normally observe in comets. Either this is natural chemistry taken to an extreme, volatiles outgassing with unprecedented vigour in an interstellar visitor with unusual composition, or this is something else. Something that doesn't fit the comet template at all. Something that forces us to consider options outside the comfortable catalogue of solar system objects. And that brings us to the hypotheses, the competing frameworks, the explanations that range from prosaic to paradigm shifting. Let's lay them out plainly and see which one survives contact with the data. Part 5. Implications and immediate hypotheses. 3 hypothesis buckets, 3 possible explanations for what we're seeing. Each comes with predictions, each comes with tests. Let's be clear about what we're claiming and what we're speculating. Hypothesis A is natural super-volatile comet. This is the baseline, the null hypothesis, the explanation that requires the least upheaval to existing theory. 3I-ATLAS formed in another star system with a composition different from solar system comets. Maybe higher refractory content. Maybe richer in carbon monoxide, carbon dioxide, molecular oxygen. It spent millennia in interstellar space, cold and inert, before falling into our solar system. As it approached the Sun, intense solar heating triggered violent outgassing of super-volatile ices that sublime at low temperatures. The rapid brightening reflects explosive sublimation. The blue colour comes from molecular emission, CN, C2, oxygen lines, or CO2 fluorescence populating the coma with blue-emitting species. The extended luminous envelope is just a massive gas cloud, energised by solar UV, radiating across hundreds of thousands of kilometres. Spherex's earlier detection of CO2 in August supports this. Carbon dioxide was already present months before perihelion, proving the object carries volatiles. If CO2 ice was abundant and then got flash heated near perihelion, you'd expect a surge in outgassing. Models suggest super-volatile ices can produce steep brightness curves under the right conditions, not negative 7.5 steep in most simulations, but steeper than water-dominated comets. Maybe 3I-ATLAS just pushed the volatile-driven brightening to an extreme we haven't seen before because interstellar objects have compositions outside our experience. Expected observational signatures for this hypothesis include specific emission lines in the visible and infrared spectrum. Carbon monoxide has strong IR bands around 4.7 microns. Carbon dioxide has bands around 4.3 microns and 15 microns. Cyanogen has UV to violet lines. Diatomic carbon has green lines. If hypothesis A is correct, Hubble and Webb should detect these lines when they observe 3I-ATLAS in December. The spectrum should look like a gas cloud, not a reflection spectrum. Gas-to-dust ratios should be high. The object should show strong non-gravitational acceleration, as the outgassing exerts thrust, pushing the nucleus off its purely gravitational orbit. Hypothesis B is exotic physical process. This keeps the object natural, but invokes less familiar mechanisms. Plasma fluorescence driven by solar wind electrons exciting atoms and ions to high-energy states, which then emit visible light. Dust grain charging, creating luminescence as charged particles interact with the grain surfaces. Magnetic field interactions if the object somehow carried a remnant magnetic field from its formation environment, coupling to the solar wind and generating emissions. These are speculative but not impossible. We've seen plasma processes create auroras on planets, glow in planetary magnetospheres, emit X-rays from comets, when solar wind ions collide with cometary gas. The catch is scale. Auroras on Earth are bright but localized. Cometary X-ray emission is faint, requiring sensitive detectors. To produce visible light bright enough to appear bluer than the Sun, in coronagraph photometry requires intense energy deposition. Solar wind electron fluxes near the Sun are high, but converting that energy into visible emission efficiently demands specific conditions: high gas density for electrons to collide with, the right atomic and molecular species with accessible excited states, geometries that enhance emission, like bow shocks or magnetic cusps focusing electrons. Predicted observations for hypothesis B include ion emission lines, signatures of ionized oxygen, carbon, nitrogen, non-thermal emission that doesn't match blackbody curves, polarization patterns consistent with scattering in a magnetized plasma, variability tied to solar wind conditions, since electron fluxes change with solar activity, rapid temporal changes, as plasma processes respond to fluctuations in the solar wind faster than thermal processes respond to heating. Hypothesis C is engineered activation. This is the speculative end, the uncomfortable what-if, the hypothesis that makes mainstream astronomers wince but can't be dismissed without evidence. If 3I-ATLAS were a fragment of manufactured material, designed to endure stellar encounters, it might employ refractory alloys that don't sublimate, coatings that fluoresce under intense UV or heat, mechanisms that activate only under specific energy thresholds, like solar flux exceeding a trigger level. The rapid brightening and blue emission could be deliberate, a response programmed into the material's structure. Why would anything be designed that way? Speculation piles on speculation here. Maybe it's a probe, maybe it's debris from some long-dead civilization's construction project. Maybe it's a signalling device meant to announce its presence when bathed in starlight. Or maybe it's just wreckage, unintentional activation of systems never meant to operate this way. None of this is evidence. It's thought experiment. But thought experiments are how science explores parameter space, before data constrain the options. Observational signatures for hypothesis C are tricky. If engineered, the object might show structural regularity in high-resolution imaging, geometric shapes, symmetries, non-random fragmentation patterns if it breaks apart. Spectra might reveal materials with unusual compositions, refractory elements in ratios that don't match natural formation pathways, narrow-band emission lines that don't correspond to known atomic or molecular transitions, hinting at artificial phosphors or engineered emitters. Telemetry like periodic signals would be a smoking gun, but that's extremely unlikely. No one seriously expects 3I-ATLAS to be broadcasting. For each hypothesis, follow-up. Observations will supply decisive tests. Spectroscopy is the key. High-resolution spectra across visible, UV, and infrared will reveal whether the blue light comes from CN and C2 gas emissions, hypothesis A, or from something more exotic. Polarimetry will constrain dust properties and magnetic field orientations. High-cadence imaging will track rapid structural changes or variability patterns. Radar, if geometry allows, could probe for dense, solid structures inconsistent with a rubble pile comet nucleus. Risk assessment matters. If hypothesis C were true, if we're dealing with an engineered object, what are the consequences? Most likely no immediate threat. 3I-ATLAS isn't headed for Earth impact. Its closest approach is December 19th, 0.93 AU, still outside Earth's orbit. Even if it were designed, that doesn't imply intent to harm. It could be passive, inert, a relic. The scientific and philosophical implications would be profound, but the practical dangers minimal. Reassurance without dismissal. Historical parallels help frame this. 1I/Oumuamua, the first confirmed interstellar object, showed non-gravitational acceleration without visible outgassing. That was weird. Models struggled. Avi Loeb proposed a solar sail, an engineered light sail pushed by radiation pressure. Mainstream scientists favoured exotic ice sublimation, hydrogen icebergs, nitrogen ice. Neither explanation was fully satisfying. 2I/Borisov, the second interstellar visitor, behaved like a classical comet. Familiar chemistry, fragmentation, outgassing. No surprises. 3I-ATLAS might be a third category. Different from Oumuamua's inertness, different from Borisov's normalcy. A new class. Interstellar visitors have surprised us before. Each one taught us something. Oumuamua taught us that tumbling elongated objects can visit from other stars and that not all comets outgas visibly. Borisov taught us that some interstellar comets look just like ours, validating the universality of cometary processes. 3I-ATLAS, whatever it is teaching us that the frontier still holds mysteries, that our models are provisional, that nature or something else can still deliver shocks. The data quality question looms. Is this a real physical mystery or a measurement mirage? That's what Act 2 will dissect. We'll pull apart the instruments, scrutinise the calibrations, confront the skeptics, and map the competing camps. We'll dive into the other anomalies, the anti-tail growth, the orbital residuals, the missing early flares. We'll reconcile the contradictions or expose them as irreconcilable. And by the end, you'll know whether 3I-ATLAS is rewriting the textbook or just testing our patience. The mystery deepens, the instruments have spoken, now it's time to listen harder. Part 6. Reconciling with other anomalies. 3I-ATLAS didn't just surprise us at perihelion. The object has been delivering anomalies for months, and not all of them fit neatly into a single narrative. Let me list what else we've observed. An anti-tail that reportedly grew from 600 to 720 kilometers in 24 hours. Orbital residuals showing tiny earthward pulls, astrometric positions deviating from pure gravitational predictions by fractions of an arc-second. Earlier reports suggesting minimal perihelion flare in some datasets, contradicting the explosive brightening coronagraphs captured. These aren't minor details. They're pieces of a puzzle that might not come from the same box. The timeline matters. Weeks to months before perihelion, ground telescopes tracked 3I-ATLAS as it descended toward the Sun. Observations showed modest activity, some dust production, nothing alarming. Then came the August Sphere-X detection of carbon dioxide, establishing volatile content. Then came late October, perihelion passage, and the coronagraph fireworks. Now we're in early November, waiting for the object to re-emerge from solar glare so Earth-based instruments can resume tracking. Different instruments sampled different epochs, different phenomena at different times. Are these contradictions or complementary observations? 3 scenarios present themselves. First scenario is that different instruments were sampling different phenomena. Coronagraphs see brightness and colour. Ground telescopes see dust and tail morphology. Astrometric observations track position. Each measures a different aspect of the same object, and those aspects don't have to behave identically. A comet can brighten explosively while its dust tail remains stable. Gas emission can dominate light output even if dust production stays modest. There's no law saying all observables must change in lockstep. Second scenario is that the object changed behaviour abruptly near perihelion. Maybe 3I-ATLAS was relatively dormant for months, then something triggered at close solar distance. Thermal stress cracking the surface, pressure build-up releasing suddenly, phase transition in subsurface ice, an activation threshold if we're entertaining the engineered hypothesis. Objects can undergo state changes, comets fragment, asteroids crack. If 3I-ATLAS transitioned from one regime to another, early observations and perihelion observations would look contradictory even though both are accurate snapshots of different states. Third scenario is that some earlier observations were misinterpreted. Photometry is hard, tail measurements are hard. Astrometry is extremely hard when dealing with faint diffuse objects near the Sun. Maybe the reported minimal early flare was actually measurement error, the object lost in noise or confusion with background stars. Maybe the anti-tail growth was a viewing geometry illusion, not real mass ejection. Maybe the orbital residuals were statistical flukes, noise masquerading as signal. Misinterpretation doesn't mean incompetence. It means working at the edge of instrumental capability where errors are easy and confirmation is slow. Let's examine the anti-tail growth specifically. An anti-tail is an optical illusion. Dust particles ejected from a comet don't move straight back from the Sun. They follow slightly curved orbits, lagging behind the nucleus. When Earth's viewing angle is just right, we see those lagging particles projected against the sky in a way that looks like a tail pointing toward the Sun. An anti-tail. It's geometry, not physics. The particles aren't actually moving sunward. We're just seeing them from an angle that creates that appearance. The reported growth from 600 to 720 kilometers in 24 hours suggests either the dust distribution changed or our viewing angle changed. Viewing geometry shifts slowly over days as Earth and the comet move in their orbits. A 120-kilometre apparent change in one day is faster than geometry alone would predict, hinting at real dust dynamics. Maybe fresh dust was ejected in a burst, populating the anti-tail region. Maybe existing dust accelerated under radiation pressure, spreading the tail spatially. Either way, anti-tail behaviour is about dust. The perihelion brightening is about gas emission and possibly small dust. These could coexist without contradiction. Orbital residuals are trickier. Astrometry measures where an object appears on the sky. Ephemerides predict where it should appear based on gravitational forces alone. Residuals are the differences. Positive residuals in the earthward direction mean the object is slightly closer to Earth or slightly ahead in its orbit compared to predictions. The reported values, plus 0.37 arc-seconds growing to plus 0.43 arc-seconds, are tiny, a fraction of a pixel in most telescope images. Measuring those requires precise calibration and careful removal of systematic errors. What causes non-gravitational residuals? Outgassing jets produce thrust. A comet venting gas preferentially in one direction experiences a rocket effect, a tiny push that accumulates over time. Radiation pressure from sunlight pushes lightweight dust particles, and if the comet is shedding dust asymmetrically, the nucleus can recoil. Microthrust from mass loss, even if the mass loss is symmetric, can produce net forces if the nucleus is rotating, and jets turn on and off with rotation. All these mechanisms are understood. We see them in solar system comets routinely. The puzzle is connecting residuals to brightening. If 3I-ATLAS underwent violent mass ejection at perihelion, reducing the steep brightness curve, we'd expect substantial non-gravitational acceleration. Gas jetting at high velocity carries momentum. Losing mass changes the orbit, but the reported residuals are small, subtle, maybe not even significant given measurement uncertainties. That's odd. Explosive outgassing should produce detectable thrust. If it doesn't, either the outgassing was mostly isotropic, symmetric in all directions so force is cancelled, or the brightening wasn't due to mass ejection at all. Here's a possible reconciliation. Suppose the blue emission came from gas fluorescence, not from scattering off freshly ejected dust. Gas molecules absorb solar UV, reach excited states, emit visible light, and fall back to ground states. That process radiates light but doesn't require mass loss in the sense of material leaving the nucleus permanently. The gas can expand, emit, and then be ionized or dissociated by solar wind without producing net thrust on the nucleus if the expansion is symmetric. You'd see brightness without acceleration. Alternatively, if the brightening involved emission from a reflective or fluorescent surface rather than mass ejection, you'd definitely see brightness without thrust. Engineered materials that glow under UV wouldn't shed mass, they'd just radiate. That fits hypothesis C but requires us to accept the engineered premise, which remains speculative. Compared to 1I/Oumuamua, that object showed measurable non-gravitational acceleration without visible coma or tail, no dust, no gas. The acceleration was real, confirmed by multiple observatories, statistically significant, yet no outgassing signature. Explanations range from hydrogen icebergs sublimating invisibly to solar sails catching radiation pressure. The tension between acceleration and lack of visible activity defined the Oumuamua mystery. 3I-ATLAS might present the opposite tension. Visible activity, dramatic brightening, but minimal acceleration. Inverse Oumuamua. 2I/Borisov, for comparison, behaved classically. Brightening matched outgassing. Non-gravitational forces matched visible dust and gas production. Fragmentation events corresponded to brightness changes. Everything made sense. Borisov was normal. Oumuamua was weird in one direction. 3I-ATLAS might be weird in another direction. Each interstellar visitor carving out its own niche in the taxonomy of strangeness. Potential data mismatch reasons abound. Spatial resolution varies wildly between instruments. Ground telescopes resolve the nucleus and inner coma. Coronagraphs see extended envelopes, but blur fine details. Different spatial scales sample different physical processes. Spectral sensitivity matters too. Visible light instruments miss infrared emission. UV instruments miss red light. An object glowing brightly in one wavelength range might appear faint in another. Observation geometry changes everything. The angle between sun, object and observer determines what dust features are visible, what gas emissions are Doppler shifted, how tails project on the sky. Reconciling these contradictions requires instrument teams to publish detailed calibrations, observation logs, and processing methods. Independent analysts need access to raw data. Comparisons must account for different sensitivities, different observation times, different fields of view. This is slow work. Weeks to months. Peer review takes time, but it's essential. Rushed conclusions about anomalies have a way of evaporating when scrutiny increases. The question we're left with is whether 3I-ATLAS is genuinely anomalous or merely confusing. Anomalous means the physics doesn't fit. Confusing means the observations don't fit yet because we haven't understood them properly. History has examples of both. Pulsars were anomalous until we discovered neutron stars. Fast radio bursts were confusing until we got better localizations and identified host galaxies. Some mysteries resolve into new physics, some resolve into better measurements. Where does 3I-ATLAS fall? We won't know until the instruments are scrutinized, calibrations are verified, and the observation campaign continues through December. The next step is to confront the skeptics, to examine the calibration risks that could make all this drama dissolve into instrumental artifact. Because if the coronagraphs were wrong, if the brightness curve and colour shift are illusions born of stray light and bad background subtraction, then we're chasing ghosts, and we need to know that before we rewrite textbooks or declare paradigms shifted. Skepticism isn't obstruction, it's due diligence. Let's see what the doubters have to say. Part 7. Instrument team skepticism and calibration risks. Professional caution is not cowardice, it's survival. Mission teams running Stereo, SOHO, GOES didn't build billion-dollar spacecraft to make hasty claims about interstellar comets. They built them to study the sun, monitor space weather, and track coronal mass ejections. When something unusual appears in their data, their first instinct isn't to publish, it's to check, double-check, triple-check. Make sure the signal is real before attaching your name and your mission's reputation to a claim that could be wrong. This is good scientific practice. It's how you avoid embarrassment. It's how you maintain credibility over decades. The chronograph teams have seen plenty of weird signals over the years. Dust grains hitting the detector, cosmic rays streaking through frames, electronic glitches creating ghost images, stray light from planets, bright stars or internal reflections. Most anomalies are mundane once you dig into them. The hard part is distinguishing the one real signal from the 99 false positives. Calibration issues for coronagraphs are numerous and technical. Stray light is the chronic enemy. Sunlight scatters inside the instrument, bouncing off baffles, diffracting around edges, reflecting from optical surfaces. Even with careful design, some fraction of solar photons ends up where they shouldn't, contaminating the image. Stray light patterns are complex, varying with the sun's position relative to the instrument, with the spacecraft's orientation, with thermal conditions affecting optical alignment. Correcting for stray light requires detailed models built from years of in-flight calibration data. Vignetting changes colour ratios across the field of view. The detector's sensitivity isn't uniform. Edges are less sensitive than the centre. Different filters vignetize differently because lens coatings and detector quantum efficiency vary with wavelength. An object at the edge of the frame might appear artificially red or blue compared to one at the centre, not because of real colour differences, but because of instrumental response. Flat fielding corrects for this by imaging uniform sources and dividing science frames by the flat field, but flats are never perfect. Pixel nonlinearity means bright sources don't scale correctly. Detectors are designed to respond linearly to light. Twice the photons should produce twice the signal, but at high or low signal levels, detectors deviate from linearity. Bright objects saturate, clipping the signal at the maximum pixel value. Faint objects hit noise floors where red noise and dark current dominate. Nonlinearity curves must be measured and corrected, and those corrections carry uncertainties. Saturation is particularly nasty. Once pixels max out, you've lost information. You can't recover the true brightness. You can try to estimate it by fitting wings of the point spread function, using unsaturated pixels nearby to infer the central brightness, but that's model dependent and error prone. If 3I-ATLAS saturated the detector during perihelion, brightness measurements become guesses, not data. Cosmic ray hits mimic real sources. high-energy particles from space strike the detector, depositing charge that looks like a bright spot or streak. Single-frame cosmic rays are easy to reject by comparing consecutive frames. If a bright spot appears in one frame but not the next, it's probably a cosmic ray. But if cosmic rays hit repeatedly in the same region by chance, or if the object you're tracking happens to overlap cosmic ray hits, confusion arises. Sunlight scattering in the optics creates artifacts that can look like extended sources. Diffraction spikes, lens flares, ghost reflections. Coronagraphs minimize these with careful baffle design and multiple occulting disks, but they can't eliminate them entirely. A bright star just outside the field of view can scatter light that appears as a faint halo inside the image. The sun's own diffraction pattern, even when the disk is occulted, produces faint rings and spokes. Distinguishing a real comet coma from a scattering artifact requires experience, and often multi-epoch observations to confirm the source moves with the expected comet motion. Science teams mitigate these problems with standard techniques. Flat fielding corrects vignetting. Dark frame subtraction removes detector bias and thermal noise. Cosmic ray rejection algorithms clean up single-frame hits. Background modelling subtracts the average corona and leaves the moving object. Temporal coherence. Checks verify that brightness tracks smoothly over time. Multi-instrument comparisons catch systematic errors that affect one sensor but not others. The significance of cross-confirmation between independent instruments can't be overstated. Stereo A, SOHO, GOES-19 have different optical designs, different detectors, different calibration histories, different orbital positions. An artifact affecting one shouldn't affect all three in the same way. If all three report a steep brightness curve and blue colour, you'd need a conspiracy of errors. Stray light contaminating stereo's blue filter. Vignetting biasing SOHO's colour measurement. Background subtraction failing identically on GOES. Possible? Yes. Likely? No. Each added confirmation makes the artifact hypothesis less tenable. But critics might say coronagraph colour indices aren't reliable for faint moving objects. They might argue that coronagraphs are optimised for extended coronal structures, not point sources. That photometry of small comets is at the edge of capability. That converting detector counts to calibrated flux involves assumptions about spectral shape, and those assumptions break down if the object's spectrum is unusual. All valid points, all worth investigating. Historical precedents exist for coronagraph misreads. SOHO-LASCO once detected features that were initially thought to be interesting coronal structures but later identified as dust grains on the detector faceplate. Bright comets passing through the field have sometimes produced artifacts that looked like secondary tails or companion objects, later explained as optical ghosts. Modern teams are better at catching these because they've learned from past mistakes, but perfection remains elusive. The procedural steps the community will take are unfolding now. Private instrument team reviews are underway. Experts at the Naval Research Lab, which runs LASCO, and at the Stereo and GOES teams are examining raw frames, checking calibration files, running independent photometry. Papers with calibrated flux conversions and detailed error analysis are in preparation. Community replication will follow once data are publicly released. Amateur astronomers and professional skeptics will download the frames and run their own analyses. Consensus will emerge from that process, not from a single team's claim. Expected timescales are weeks for preliminary checks, months for full peer-reviewed publication. Science moves slower than Twitter. Hype cycles demand instant answers. Science demands patience. The tension between public curiosity and scientific rigour creates frustration. People want to know now. Is it real or not? Is it aliens or not? Science says, we're working on it. Check back in February when the papers are published and vetted. Headlines will split between controversial and confirmed depending on who you ask. Avi Loeb's advocacy for considering the engineered hypothesis makes him a lightning rod. Supporters praise his willingness to think outside the box. Critics accuse him of publicity seeking, of jumping to conclusions, of giving false hope to UFO enthusiasts. Both sides have points. Loeb has been right before, proposing ideas that were dismissed then later validated. He's also been wrong, staking claims that didn't hold up. Science isn't about authority, it's about evidence. The data will decide, not reputations. So what would real confirmation look like? What observations would settle the question beyond reasonable doubt? Confirmation requires multiple lines of evidence converging. Spectroscopy showing anomalous emission lines that can't be explained by known cometary chemistry. High-resolution imaging revealing structure inconsistent with a natural rubble pile nucleus. Detection of periodic signals or spatial patterns indicating design. Non-gravitational accelerations that precisely match brightness changes, proving mass ejection is the cause. Or conversely, lack of acceleration proving emission without mass loss. Independent replication by multiple teams using different instruments, all agreeing on brightness, colour, and spectral features. Confirmation also requires ruling out alternatives, demonstrating that instrument artifacts can't explain the signal, showing that calibration errors would need to be implausibly large and correlated, proving that natural mechanisms, even exotic ones, fail to produce the observed combination of properties. Extraordinary claims demand extraordinary evidence, and extraordinary evidence means exhausting ordinary explanations first. The drama of real versus fake, signal versus noise, discovery versus artifact is central to modern astronomy. Every major finding goes through this gauntlet. Gravitational waves were debated for decades before LIGO's detection, and even then skeptics demanded verification. Exoplanets were controversial until Doppler surveys and transits accumulated overwhelming statistics. Fast radio bursts were suspected instrumental glitches until multiple telescopes confirmed them. 3I-ATLAS is just the latest object to enter this crucible. It will either emerge validated, a genuine anomaly demanding new models, or it will dissolve. A cautionary tale about measurement at the limits. We stand at the inflection point. The instruments have spoken, the teams are checking, the community is watching, and in the background December 19th approaches, the date when 3I-ATLAS makes its closest approach to Earth and ground telescopes finally get their chance. If the coronagraphs were right, December will bring confirmation and spectacle. If they were wrong, December will bring disappointment and lessons learned. Either way, we're about to find out. The science that settles questions like this is already in motion. Now we examine what kind of object could produce these signals naturally, and what kind of object would require us to abandon natural explanations entirely. Part 80. The origin story, natural versus engineered. Natural object or engineered artifact. Both are hypotheses. Neither is a conclusion. Let's be explicit about that framing. We're exploring parameter space, not declaring truth. Science works by proposing models, deriving predictions, comparing to observations, and iterating. Right now we have observations that don't fit standard comet models easily, so we expand the model space. Natural objects with exotic chemistry. Physical processes we've seen in principle, but never at this scale. Or, at the far end of plausibility, manufactured materials with properties no natural formation process produces. All three are on the table until evidence removes one or more. The natural origin path starts in another stellar system, millions or billions of years ago. A protoplanetary disk around a young star collapses into planets, asteroids, comets. Some objects form with compositions different from solar system bodies. Higher carbon content, more refractory organics, unusual volatile inventories. Maybe the parent star's radiation environment was different, altering ice chemistry. Maybe giant planets in that system scattered objects in ways that preferentially ejected carbon-rich bodies. We don't know the details because we've never visited another star's comet cloud, but we know chemistry varies with stellar metallicity, temperature, UV flux. Diversity is expected. Ejection happens through gravitational scattering. A planet's gravity kicks an object to high velocity, exceeding the escape speed of the star system. The object flies into interstellar space, travelling for millennia or longer. The long interstellar journey subjects it to cosmic rays, UV from the galactic background, occasional close passes to other stars. Surface chemistry changes. Organic molecules get processed. Volatiles may sublimate slowly even in the cold of interstellar space if hit by enough energetic particles. By the time the object enters our solar system, it's been modified by its journey. Then comes the encounter with our Sun. Solar gravity captures the trajectory, bending the object's path into a hyperbolic orbit. As it descends toward perihelion, solar heating increases. Temperature rises. Volatiles begin to sublimate. The object develops a coma, a tail. Brightness increases. For a typical comet, this follows well-known scaling laws. But 3I-ATLAS isn't typical. If its composition is exotic, its behaviour can be exotic too. Plausible chemistry scenarios focus on carbon-rich matrices and unusual volatile inventories. Refractory organics, complex carbon molecules that don't sublimate until very high temperatures, could dominate the bulk composition. Embedded in that matrix might be pockets of carbon monoxide, carbon dioxide, molecular oxygen, all supervolatiles that sublimate below the temperatures where water ice melts. As the object heats, supervolatiles vent first, producing gas emission without much dust. High gas to dust ratio means high brightness from fluorescence, but relatively little light scattering from solid particles. The Spherex detection of carbon dioxide in August confirms volatile presence. Carbon dioxide ice sublimates around 150 Kelvin. That's cold, much colder than the 170 to 200 Kelvin, where water ice sublimates. If 3I-ATLAS is rich in CO2 ice, it starts out gassing farther from the Sun than water-rich comets do. Closer to the Sun, CO2 sublimation accelerates explosively because the vapour pressure rises exponentially with temperature. You get a runaway, positive feedback, more heat, more gas, more heating from latent heat release, even more gas. That could drive steep brightness curves. But does it drive negative 7.5 exponents? That's where the models struggle. Simulations of supervolatile-driven comets produce steeper curves than water comets, but typically negative 5 to negative 6, not negative 7.5. Maybe 3I-ATLAS hit a threshold where subsurface pressure ruptured the crust, triggering catastrophic release. Maybe it fragmented, multiplying surface area instantly. Models that include fragmentation can produce very steep brightness spikes. The challenge is that fragmentation usually produces visible fragments, changes in morphology, dust clouds. Have we seen evidence for fragmentation in the coronagraph images? That's a question for the detailed analysis teams haven't fully published yet. Now consider the engineered hypothesis, not as belief but as structured thought experiment. If a civilization wanted to send a probe through interstellar space and have it survive close passes to stars, what design choices would make sense? Refractory materials that don't melt or sublimate, high strength to weight ratio, passive systems that don't require active control, coatings that protect against UV and particle radiation, and possibly mechanisms that respond to environmental triggers like high radiant flux by changing state in useful ways. Why would activation under extreme flux be useful? Speculation piles up here, but let's entertain it. Maybe the probe is designed to gather energy when near a star, storing it for later use. Maybe it signals its passage, intentionally emitting light to make itself visible to anyone watching. Maybe the material simply has properties that produce blue fluorescence under UV as a side effect of its protective coating, not by design but by consequence. Or maybe, and this is the most speculative angle, the object wasn't designed to visit stars at all. It's debris. A fragment from something that broke apart. It's activating in ways it was never meant to, because it's no longer part of a larger structure that regulated its behaviour. Avi Loeb and colleagues who advocate for technosignature considerations frame it as applying the same scientific method we'd use for any hypothesis. List predicted observables. Check if they're present. Update probabilities. Loeb's reasoning for 1I/Oumuamua was that its unusual geometry, high aspect ratio, and non-gravitational acceleration without visible outgassing pointed to something artificial, specifically a light sail. Critics argued natural explanations existed, hydrogen icebergs or nitrogen ice. Neither side won decisively because the data were insufficient. Oumuamua left the solar system before detailed spectroscopy could be obtained. Mainstream scientists stressed natural explanations first, and rightly so. The vast majority of astronomical phenomena have natural causes. Invoking engineered artifacts when we haven't exhausted natural possibilities is premature. Carl Sagan's dictum applies. Extraordinary claims require extraordinary evidence. A steep brightness curve and blue emission, while unusual, don't constitute extraordinary evidence for engineering. They constitute puzzling observations requiring further study, tests that could favour one hypothesis over another centre on spectroscopy and morphology. Narrowband non-thermal emission lines would be very strange. Atoms and molecules emit at specific wavelengths set by quantum mechanics. If you detect emission lines that don't match any known element or molecule, you've found something genuinely weird. That would tilt heavily toward engineered materials with artificial phosphors or novel compounds. Detection of structurally regular fragments would do the same. Comets fragment chaotically. Nuclei split along stress fractures, producing irregular chunks. If 3I-ATLAS breaks into pieces with geometric regularity, planes, symmetries, repeated structures, that's hard to explain naturally. Telemetry like periodic signals remains the ultimate smoking gun, but it's also extremely unlikely. No astronomer seriously expects 3I-ATLAS to broadcast radio or optical pulses. That would be so obvious, so unambiguous, that the question would be settled instantly. The absence of telemetry doesn't prove the object is natural, though. A defunct probe, a piece of debris, an object not designed to communicate would be silent. Silence is ambiguous. Philosophical reflection on weighing evidence brings us to Bayesian reasoning. You start with prior probabilities. How likely is it that 3I-ATLAS is engineered given what we know about the universe, the rarity of technological civilizations, the vastness of space, the number of natural objects versus artificial ones? Most people assign a very low prior, maybe 1 in a million or 1 in a billion. Then you update based on evidence. The steep brightness curve and blue emission are unusual, so they increase the posterior probability of the engineered hypothesis a little. But a little times, a tiny prior is still a tiny posterior. You need overwhelming evidence to shift a low prior probability to high confidence. Occam's razor says prefer simpler explanations. Natural chemistry is simpler than engineering because we know natural chemistry exists and produces comets routinely. We've never confirmed an interstellar artifact. Adding engineering to the hypothesis space multiplies complexity, adds assumptions about alien civilizations, their capabilities, their motivations. Unless natural explanations fail completely, Occam's razor favours natural. But Occam's razor is a heuristic, not a law. Sometimes the simpler explanation is wrong. Sometimes complexity is necessary. Pulsars seemed simple until you realise they were spinning neutron stars, which required general relativity and nuclear physics to understand. Simplicity is a guide, not a guarantee. The debate around 3I-ATLAS echoes the Oumuamua debates in tone and structure. Proponents of the artificial hypothesis ask why we should ignore a possibility just because it's uncomfortable. Opponents ask why we should entertain it when we haven't ruled out natural causes. Both are doing science. Both are applying skepticism, just in different directions. One side is skeptical of conventional models, the other is skeptical of unconventional claims. The data will mediate. Historical context shows this pattern repeating. When quasars were discovered, some proposed they were artificial beacons. They weren't. They were supermassive black holes accreting matter. When pulsars were discovered, some joked about LGM, little green men. They weren't. They were neutron stars. When the WOW signal was detected, some thought it was extraterrestrial transmission. It probably wasn't, though we still don't know for sure. Most anomalies resolve naturally, but not all, and the only way to know is to check. What happens next will tell us more than speculation can. Observations scheduled for December through January will bring high-resolution spectra, polarimetry, imaging and astrometry from instruments that weren't available during perihelion. Hubble, Webb, Keck, VLT, Gemini, all can point at 3I-ATLAS once it's far enough from the Sun. Those observations will either confirm the coronagraph findings or refute them. They'll either reveal exotic chemistry or familiar chemistry. They'll either show structure or chaos. We'll know soon, and knowing is better than guessing, even when the guess is more exciting than the answer. Part 9. What happens after perihelion? Observations and predictions. October 29th was perihelion. December 19th is closest Earth approach. That date matters because it marks the moment when 3I-ATLAS emerges fully from solar glare and enters the observational sweet spot for ground-based telescopes and space observatories. Between now and then, the object is climbing back out of the Sun's gravitational well, receding from perihelion, moving toward a geometry where Earth-based instruments have clear line of sight without fighting the Sun's overwhelming brightness. December 19th, 0.93 astronomical units from Earth. Still outside our orbit, but close. Enough for detailed spectroscopy. Close enough for imaging with angular resolution that can resolve structure if structure exists. Predictive modelling splits into two divergent scenarios, each with concrete observational signatures. Scenario A is continued brightening. If the processes driving the perihelion flare continue, if super volatile outgassing persists or accelerates, if emission mechanisms remain active, then brightness should stay elevated or even increase as the object moves through late November and early December. Magnitude estimates are model dependent, but if the negative 7.5 scaling extends post-perihelion, 3I-ATLAS could reach visual magnitudes accessible to amateur telescopes, maybe magnitude 8, maybe brighter. That would make it visible in twilight skies for observers with dark sights and decent equipment. Scenario B is rapid fade. Many comets that brighten explosively near perihelion fade quickly afterward. Fragmentation events produce spikes that collapse within days. Super volatile reserves can exhaust. If 3I-ATLAS loses its volatiles or fragments into pieces too small to track, brightness drops fast. Magnitude estimates for this scenario suggest fading below magnitude 15 by mid-December, invisible except to large professional instruments. This happened to other comets. It's not unusual, but it would be disappointing. A brief fireworks show followed by darkness, leaving us with coronagraph data and questions. Which scenario is more likely? Nobody knows. That's why December matters. Observations during the first 2 weeks of December will reveal which trajectory the object follows. If brightness holds or increases, Scenario A gains credibility. If brightness plummets, Scenario B wins. Either outcome teaches us something. Sustained brightness supports ongoing volatile outgassing or emission. Rapid fade supports explosive transient release or fragmentation. Priority observation modes for December focus on spectroscopy, polarimetry, imaging, and possibly radar. High-resolution spectroscopy across visible and infrared wavelengths is the gold standard. Spectrographs on Hubble, Webb, Keck, VLT can resolve individual emission lines with precision. They'll search for carbon monoxide lines around 4.7 microns, carbon dioxide bands around 4.3 and 15 microns, cyanogen lines in the violet, diatomic carbon lines in the green, forbidden oxygen lines at 500 nanometers. Each line tells you what molecules are present and how abundant they are. If the spectrum shows strong CO and CO2, that validates the supervolatile hypothesis. If it shows lines that don't match known molecules, that's deeply strange. Polarimetry constrains dust properties. Light scattered by small particles becomes polarized, and the degree and angle of polarization depend on particle size, shape, and composition. If 3I-ATLAS's coma is full of submicron grains producing Rayleigh, scattering, polarimetry will show high polarization percentages. If it's mostly gas with little dust, polarization will be low. Comparing polarization at different wavelengths maps grain size distributions. This is diagnostic. It separates gas emission from dust scattering, answering the question of whether the blue color comes from small grains or molecular fluorescence. High cadence imaging tracks rapid structural changes. If the object is fragmenting, pieces will separate over days, visible as distinct sources in images. If it's developing jets or asymmetric features, those will appear as brightness variations or directional tails. Time-resolved imaging at intervals of hours to days builds movies of the coma's evolution, revealing dynamics invisible in single snapshots. Hubble's high angular resolution is perfect for this. Webb's infrared sensitivity lets it see through dust and capture thermal emission that traces temperature and volatile sublimation. Radar is a wild card. If geometry allows, radio telescopes like Arecibo's replacement or Goldstone could ping 3I-ATLAS and measure echoes. Radar detects dense structures, resolves shape and rotation, measures surface roughness. A fluffy comet nucleus scatters radar weakly. A solid metallic object scatters strongly. Radar could, in principle, distinguish a rubble pile from something denser. But radar requires the object to be close and bright in radio wavelengths, and 3I-ATLAS may not meet those criteria. Still, it's worth trying. Who will observe and when? Scheduling is competitive. Hubble and Webb time is allocated months in advance through proposal processes. But both observatories allow directors discretionary time for targets of opportunity, unexpected transient events that demand immediate follow-up. 3I-ATLAS qualifies. Directors at both missions could approve DDT proposals in late November, allocating hours in December for spectroscopy and imaging. Ground facilities like Keck, VLT, and Gemini also have DDT programs. Requests are likely already submitted. Coordination among teams ensures complementary observations, avoiding duplication and maximising science return. Amateur networks play a role too. The amateur astronomy community has proven adept at monitoring comets, detecting outbursts, measuring brightness, and tracking morphology. Networks like the British Astronomical Association Comet Section or the American Association of Variable Star Observers organise campaigns. If 3I-ATLAS brightens enough, hundreds of amateur observers worldwide could contribute photometry, building a dense temporal dataset that professional telescopes can't match due to limited observing time. Crowdsourcing works. Processed data release timelines vary by mission and team. Hubble and Webb data go into archives within months, publicly accessible. Ground observatory data depend on proprietary periods set by each facility, typically 6 months to a year before public release. Preprints appear on Archive faster, sometimes within weeks of observations if teams rush. Social media spreads preliminary results even faster, though with less reliability. By January we'll have early reports. By March we'll have peer-reviewed papers. By mid-2026 the full dataset will be public and scrutinised by the community. Third, fragmentation. If images show multiple distinct nuclei or expanding debris clouds, that confirms structural disruption. Fourth, non-gravitational accelerations changing. If astrometry reveals accelerations that grow or shift direction, that traces outgassing patterns and tests whether emission correlates with thrust. Suggest a watchlist for the public. Mid-December, look toward the eastern sky before dawn, or western sky after sunset, depending on 3I-ATLAS's position. Exact coordinates will be published on astronomy websites and apps like Stellarium or Sky Safari. If brightness reaches magnitude 8 or 9, small telescopes and even good binoculars could spot it as a fuzzy patch. Don't expect naked eye visibility unless brightness exceeds magnitude 6, which is optimistic. Safety note: never observe near the sun without proper filters. Ethics note: don't claim discovery or alert without confirming with established channels. Let the professionals verify before spreading news. The potential for a public spectacle exists. Imagine twilight observations in mid-December, a faint smudge appearing in telescope eyepieces growing night by night. Amateur astronomers posting images online. Social media buzz building. Mainstream news picking up the story. Interstellar visitor glowing mysteriously. That's cultural impact. That's what a bright, weird object does to public imagination. It makes people look up. It makes them ask questions. Why is it blue? Where did it come from? Are we alone? Even if 3I-ATLAS fades and disappoints, the attempt itself teaches us about observing interstellar objects. We learn what works, what doesn't, how to coordinate campaigns, how to allocate resources for rare transient events. Future interstellar visitors will benefit from lessons learned here. And visitors will come. 1I/Oumuamua proved they arrive. 2I/Borisov proved it wasn't a fluke. 3I-ATLAS is the third. There will be a fourth, a 10th, a 100th. Each one teaches. Each one refines our methods. December 19th. Mark your calendars. By Christmas, we'll know if 3I-ATLAS continued to brighten or faded into obscurity. By New Year, we'll have spectra. By February, we'll have papers debating what it means. The story is far from over. Perihelion was Act 1. December is Act 2. The climax is coming. And the implications extend beyond one object, beyond one mystery, into the future of how we study the universe. That's where we turn next. Part 10. Wider implications for interstellar object science. Paradigms shift when exceptions accumulate. 3. I-ATLAS might be another exception, forcing us to rethink the taxonomy of interstellar visitors. We've classified objects into simple categories for decades: asteroids versus comets, rocky versus icy, active versus inert. Those categories worked when we only studied solar system objects. But interstellar visitors don't respect our taxonomy. Oumuamua was asteroid-like in some ways, comet-like in others, and anomalous in acceleration. Borisov was clearly cometary, familiar chemistry, standard behaviour. 3I-ATLAS defies easy classification. Comet-like in having volatiles and a coma, but anomalous in brightness and colour. The new taxonomy needs categories beyond our binary. Comet-like interstellar objects that behave normally, asteroid-like interstellar objects that stay inert, hybrid objects with mixed properties, and possibly a fourth category for objects that don't fit natural templates, whether because of exotic natural processes or because they're engineered. Naming that fourth category is politically loaded. Call them anomalous interstellar objects, and you avoid implying origin. Call them techno-signature candidates, and you invite controversy. Either way, acknowledging the category exists is scientifically honest. This impacts survey design. Current surveys like Pan-STARRS, Catalina Sky Survey, and soon the Vera Rubin Observatory scan for transient objects, detecting asteroids and comets by their motion against background stars. Detection rates for interstellar objects are low because they're rare and move fast. Early estimates suggested one detectable interstellar visitor per year with current surveys. Rubin will improve that to maybe 5 to 10 per year, but detection is only half the problem. Characterization is the other half. Most interstellar objects will be discovered weeks or months before perihelion, giving limited time for follow-up. Some, like 3I-ATLAS, get discovered farther out, allowing months of observation. That's ideal but uncommon. Mission planning must account for rapid response, target of opportunity programs, flexible scheduling, coordinated campaigns between ground and space assets. Investment in these capabilities pays dividends when the next weird visitor arrives. Material science and astrochemistry face updates. Current models of cometary volatiles focus on water, carbon monoxide, carbon dioxide, methane, ammonia. Those are molecules we see in solar system comets and in interstellar clouds. But interstellar space is chemically diverse. Different stellar environments produce different ice chemistries. Super volatile-rich comets, refractory organic-rich bodies, carbon-dominated matrices, all plausible. Expanding volatile and refractory libraries means laboratory work measuring sublimation curves, fluorescent spectra, and thermal properties of exotic ices and organics. Sublimation models under extreme radiation also need refinement. Near perihelion, solar flux is intense. UV photons shred molecules. Thermal gradients drive subsurface flows, pressure builds. Current models work for water ice at moderate temperatures, but struggle with supervolatiles at high flux. 3I-ATLAS pushes the boundary, testing whether models predict its behaviour or fail. If they fail, we iterate, adding physics we've neglected. Non-Earth-like chemistries matter. Life on Earth biases our thinking toward carbon, oxygen, nitrogen, water. But comets don't care about biology. Interstellar comets even less so. Exotic molecules, polymers, organics we've never synthesized in labs might be common elsewhere. Spectroscopy that finds unfamiliar emission lines forces us to identify new compounds, expanding the known inventory of cosmic chemistry. Survey strategy improvements focus on short-window phenomena near the Sun. Coronagraph networks are undervalued. SOHO and STEREO were designed for solar physics, yet they've discovered thousands of comets incidentally. Dedicated coronagraph constellations optimized for transient detection could catch objects like 3I-ATLAS reliably. Smallsats with wide-field coronagraphs, positioned at multiple Lagrange points, would provide continuous coverage. Cost is modest compared to flagship missions. Science return is high. Rapid response telescopes, robotic systems that can slew to targets within minutes, enable early spectroscopy. By the time humans schedule observations, critical windows may close. Autonomous systems reduce latency, maximizing science from fleeting events. Ground-based networks like ATLAS and Zwicky Transient Facility demonstrate this. Expanding such networks globally ensures 24-hour coverage. Policy and messaging dimensions matter. How scientists communicate uncertainty shapes public perception. Oumuamua taught us that ambiguous findings get sensationalized. Headlines scream alien probe while papers say more data needed. 3I-ATLAS is heading down the same path. Responsible communication means stating what's known, what's uncertain, and what's speculative. Clearly labeling hypotheses as hypotheses, not conclusions. Pushing back against hype without stifling legitimate inquiry. Mission concepts this motivates include rapid, deep space interceptors. Imagine a smallsat on standby, ready to launch when an interstellar object is detected. Delta-V requirements are steep for intercepts, but not impossible. Proposals like Comet Interceptor, approved by ESA, demonstrate feasibility. Scaling that concept to interstellar targets requires faster response and higher velocity, but uses similar technology. A swarm of small probes could rendezvous with an interstellar visitor, sampling composition, imaging structure, measuring properties in situ. Data returned would answer questions definitively, no ambiguity. High-frequency solar coronagraph constellations are cheaper and more practical near-term. Deploying a dozen small sats with coronagraphs across cislunar space or at Lagrange points provides redundant coverage of the inner solar system. When objects pass near the Sun, multiple spacecraft observe simultaneously, enabling parallax, multi-wavelength coverage and cross-calibration. Cost per satellite is tens of millions. Total constellation cost is under $1 billion. Compare that to flagship missions costing billions for single targets. Cultural exploration follows. If 3I-ATLAS were confirmed as engineered, humanity's worldview shifts. We're not alone. Intelligence exists beyond Earth. That realization reshapes philosophy, religion, science funding, international cooperation. Even if natural, the mystery of its behavior reminds us the universe holds surprises. Humility is appropriate. Curiosity is essential. Our models are provisional. Nature or someone else keeps teaching. Act 2 ends with unsolved tensions, brightening without clear thrust, emission without fragmentation, blue color without confirmed molecular identification. Natural versus engineered, still unresolved. These tensions set up Act 3, where we broaden context by connecting 3I-ATLAS to other 2025 scientific anomalies and discoveries. Because science doesn't happen in isolation. Breakthroughs cluster, anomalies cross-pollinate, and understanding one mystery often illuminates others. Part 11. James Webb Hubble Discovery Highlight. Webb continues to surprise us. 2025 brought detections nobody predicted. Exoplanet atmospheres analysed by Webb's near-infrared spectrograph revealed unexpected molecular signatures. One system showed methane absorption bands coexisting with oxygen, a combination thermochemistry says shouldn't persist in equilibrium. Models scrambled to explain disequilibrium chemistry driven by photochemistry or vertical mixing. Another system displayed emission features tentatively attributed to complex organics, molecules too heavy to expect in hot Jupiter atmospheres. If confirmed, those organics challenge formation theories and suggest chemistry pathways we've overlooked. The parallel to 3I-ATLAS is methodological. Both involve remote spectroscopy revealing surprises. Both forced rapid model revisions. Webb's high-resolution infrared spectroscopy detects molecules by their absorption or emission lines. Same principle coronagraphs use for color photometry, but with far greater precision. When molecules appear that don't fit templates, scientists question assumptions. Are the lines real or artifacts? Are calibrations correct? Are models incomplete? Exoplanet atmospheric retrieval codes invert spectra to infer composition, temperature, pressure profiles. Those codes assume certain physics, certain chemistry. When assumptions fail, retrievals produce nonsense or flag inconsistencies. 3I-ATLAS's spectrum, once obtained in December, will undergo similar analysis. Spectral lines will be matched against databases. Anomalies will force new hypotheses. If familiar molecules explain everything, confidence grows in natural origin. If unfamiliar features appear, questions multiply. Practical crossovers exist between fields. Techniques developed for exoplanet atmospheres, forward modelling emission and absorption, Bayesian retrieval, error propagation, apply directly to small body spectroscopy. Software tools are portable. Expertise transfers. Collaborations between exoplanet scientists and solar system astronomers accelerate progress. 3I-ATLAS could benefit from this cross-pollination, borrowing analytical methods proven on exoplanets. Cultural angle matters. Public reaction to unexpected science discoveries on social media amplifies quickly. Webb's exoplanet findings generated headlines like "Strange molecules detected in alien atmosphere." 3I-ATLAS generates mysterious interstellar comet glows blue. Both feed curiosity. Both risk oversimplification. Scientists respond by clarifying, providing context, tempering hype without dismissing excitement. Balance is hard. Too cautious and you lose public interest. Too bold and you undermine credibility when results don't hold. The hope is that advanced observatories exist now to catch surprises early. Webb launched in 2021. Rubin Observatory is starting operations. Next-generation radio telescopes like SKA are coming online. We're entering an era where instrumental capability outpaces theoretical preparation. Surprises become routine. 3I-ATLAS is one beneficiary of this era. Coronagraphs, though not cutting-edge, provided data no ground telescope could. Future visitors will have even better coverage. The pipeline from detection to characterization to understanding shortens every year. Part 12. Pulsar Timing Array, Gravitational Wave Background Update. Nanograv and International Pulsar Timing Arrays reported hints of a stochastic gravitational wave background in 2023. Follow-up through 2025 strengthened the signal. Gravitational waves at nanohertz frequencies create correlated timing residuals in pulsars distributed across the sky. Arrays monitor dozens of millisecond pulsars, measuring arrival times of pulses with nanosecond precision. Deviations from predicted arrival times, correlated between pulsars according to specific angular patterns, signal gravitational waves stretching and compressing spacetime as they pass through the solar system. The detected background likely originates from supermassive black hole binaries, pairs of black holes orbiting in distant galaxy centers. Population models predict such binaries generate gravitational waves continuously, creating a stochastic background. But the amplitude observed is higher than some models predicted, forcing re-evaluation of black hole merger rates, galaxy evolution, and dynamical friction in galactic nuclei. Conceptual parallel to 3I-ATLAS exists. Both involve detecting faint, unexpected signals in noisy data. Both require years of careful observation and statistical analysis. Both challenge existing models. Pulsar timing arrays opened a new low-frequency window on the universe. Coronagraphs, though older technology, provided a unique window on perihelion events hidden from Earth. Frontier science pays dividends when researchers listen for faint anomalies and take them seriously. Pulsar timing anomalies could have been dismissed as instrumental noise. Collaborations chose to investigate rigorously. Redundancy across dozens of pulsars and multiple observatories ensured the signal wasn't local interference. Similarly, 3I-ATLAS's coronagraph detections gained strength from redundancy across 3 independent spacecraft. Both cases demonstrate how cross-checks validate or refute claims. Broader epistemic lesson applies. Prepare for anomalies, build redundancy into detection systems, don't dismiss outliers reflexively. History shows unexpected signals sometimes revolutionize fields. Pulsars themselves were unexpected, quasars were unexpected, gamma-ray bursts were unexpected. Each opened new areas of study. Gravitational wave backgrounds and interstellar comet brightness anomalies might seem unrelated, but they share a discovery culture, one where surprise is expected and investigation is rigorous. Part 13. AI-driven sky survey anomalies. Every night the sky changes, subtly, imperceptibly, and machines are now the first to notice. Across the world, machine learning algorithms scan millions of astronomical images, comparing pixel by pixel against previous nights. They hunt for the unexpected, a flash, a flicker, a movement, something new where nothing existed before. This process, known as transient detection, has become one of the most data-intensive automated frontiers of modern astronomy. The Zwicky Transient Facility, ZTF, at Palomar Observatory in California is one of the leading players. Every night its wide-field camera surveys the entire northern sky, producing over 1 terabyte of imaging data in a single session. Each image is instantly processed by AI-driven pipelines that subtract older reference frames, revealing what's changed. Those changes could be a supernova, a near-Earth asteroid, or a faint variable star flickering in the dark. Most of these detections are routine, but occasionally the algorithms flag something different, a transient that doesn't fit any known category. Its brightness curve doesn't follow the expected pattern, or it moves too erratically for a typical comet. These are the moments that matter, the rare outliers that might point to something genuinely new in the universe. This automation is crucial because humans simply can't keep up. The upcoming Vera C. Rubin Observatory in Chile, set to fully begin operations soon, will collect up to 20 terabytes of data per night, cataloguing billions of celestial objects. Even with thousands of astronomers, no human team could inspect every light curve or motion track. That's where AI steps in, tirelessly sorting, classifying and ranking every anomaly. But here's the catch. AI can accelerate discovery or generate convincing illusions. Machine learning models, particularly neural networks, are excellent at identifying patterns they've been trained on. A network trained on known comets, for example, learns to expect specific behaviours: gradual brightening, steady colour change, predictable tail evolution. Yet these same systems often fail when faced with something truly novel. When an object behaves outside the rules, say, brightening 7 times faster than expected, or shifting to a colour bluer than the sun, the system may hesitate, confused. It doesn't know what it's looking at. That's where 3I-ATLAS enters the picture. Imagine an early warning system trained on tens of thousands of comet-like curves. Every known comet from the Oort cloud and beyond contributes to its neural model of normal. Then, one night, data streams in from the SOHO or stereo spacecraft, showing an object whose brightness scales not as the expected R4, the classic comet law, but closer to R7.5, an absurdly steep curve. The algorithm compares this to its database, assigns an anomaly score and flags it for human review. Within hours, astronomers receive an alert, an interstellar object behaving unlike any comet we've ever seen. This is where AI's speed becomes humanity's advantage. Machines can process and cross-reference data from multiple observatories within minutes, something that would take human analysts days, and in transient astronomy, hours matter. Many phenomena, from outbursts to disintegrations, evolve on that timescale. If 3I-ATLAS were to suddenly fragment or release a bright plume of gas, automated systems could catch it while it's happening, not after it's gone. The Catalina Sky Survey, Atlas Network and ZTF have already proven this approach works. They rely on anomaly detectors and real-time alert systems that trigger rapid follow-up observations across the globe. For 3I-ATLAS, similar systems may have been responsible for the earliest reports of its unexpected brightening during perihelion, when it should have been hidden behind the sun. But AI doesn't just flag the strange, it also filters out the noise. Coronagraphs and heliospheric images, like those on GOES 19 and SOHO LASCO, are notoriously tricky to interpret. They capture light scattered through the solar corona, filled with streaks, cosmic ray hits, and instrument artifacts. Over decades, machine learning models have been trained on these datasets to recognize and remove false signals, the optical ghosts of the sun's glare. Neural networks can learn the telltale patterns of electronic noise or internal reflections, dramatically improving signal-to-noise ratios for faint objects near the sun's edge. Without that, 3I-ATLAS's faint blue envelope might have been dismissed as a camera glitch. And here's where speculation creeps in, the kind that keeps both scientists and dreamers awake. What if anomaly detection systems could do more than find supernovae or asteroids? What if, one day, they identified signals that didn't look astrophysical at all? This isn't science fiction. Modern pipelines already perform spectral anomaly detection, analysing thousands of light curves for unusual periodicity or narrowband emissions. A natural star or comet's brightness variations follow well-understood physical rhythms, but if an object emitted light at non-astrophysical frequencies, or if its pattern of brightening repeated with mathematical precision, AI could flag it as non-natural, even if human eyes missed it. Imagine this applied to interstellar objects. Suppose a future 3I-ATLAS-like visitor displayed modulated emission, subtle, repeating pulses or reflectivity changes inconsistent with rotation or gas jets. The algorithm wouldn't know it had found something artificial. It would simply flag it as a high-priority anomaly. Then the question would shift from what is it to who built it. That's the speculative frontier of technosignature search, and it's not as far-fetched as it sounds. The Breakthrough Listen project already employs deep learning systems to scan radio spectra for unusual signals. Optical astronomers are beginning to do the same with light curves, hunting for artificial flickers among billions of natural ones. AI doesn't care why something is weird, it just notices that it is. Visually, think of a network of automated observatories, orbiting telescopes, ground-based cameras and solar monitors, all linked by AI pipelines. Each night, thousands of potential anomalies stream in. The AI sorts them by statistical strangeness, pushing the most unusual into a rapid response queue. Within minutes, astronomers can decide whether to trigger an emergency follow-up, to point Hubble, Webb, or a major ground telescope toward the event. The stakes are high. A false positive wastes precious time and resources, but a missed detection could mean losing one of the most extraordinary discoveries in decades. This balance between sensitivity and specificity, between seeing everything and not crying wolf, is one of the central challenges of AI-driven astronomy. It's governed by the tuning of model parameters, the selection of training data, and constant feedback between machine and human. In essence, it's a dialogue between two kinds of intelligence, one algorithmic, one intuitive, each teaching the other what unusual truly means. And in this new landscape, objects like 3I-ATLAS are the perfect test cases. They lie at the edge of the familiar, forcing both human scientists and machine learning systems to redefine what they consider possible. When an interstellar visitor brightens faster than any comet and glows bluer than the sun, the algorithms don't just flag an anomaly, they confront us with a deeper question. Are we looking at nature's extremes, or something beyond our current understanding of nature itself? In that way, AI has become more than just a tool. It's a new kind of astronomical sense, one that doesn't blink, doesn't tire, and never forgets. As the night sky fills with data, it's the machines that will first notice when the universe decides to do something no one saw coming. Part 14, Breakthrough Mission Announcement, Update. Rapid Response Interceptor concepts gained traction in 2025 mission planning circles. Proposals submitted to NASA, ESA, and private foundations outlined smallsat interceptors designed for launch on short notice when interstellar objects are detected. Delta-V requirements depend on target trajectory. Objects passing through inner solar system need less delta-V than those staying in outer regions. Typical intercept mission requires 5 to 15 km per second velocity change beyond Earth escape, achievable with ion propulsion or chemical stages. Technical requirements include onboard spectrometers, sampling visible and infrared wavelengths, cameras for imaging at multiple scales, mass spectrometers for composition, dust collectors for particle capture. Communications relay data to Earth continuously. Mission duration from launch to encounter is months to years, depending on target distance and relative velocity. Power comes from solar panels near Sun, RTGs farther out. Relating to 3I-ATLAS, an agile mission could have launched in August when the object was discovered, arriving near perihelion for close flyby. Instruments would sample the coma composition directly, image the nucleus at meter resolution, measure non-gravitational forces in situ. Data returned would eliminate ambiguity. No more guessing about colour photometry or brightness laws. Direct measurement settles questions decisively. Real mission precedents exist. Comet Interceptor, approved by ESA for launch in 2029, demonstrates concept. It will rendezvous with a long-period comet on first inbound pass, studying pristine material. DART mission impacted asteroid Dimorphos, proving rapid targeting capability. Hayabusa missions returned samples from asteroids, showing sample return is feasible for small bodies. Combining these capabilities into an interstellar interceptor is technologically ready. What's missing is funding commitment and rapid launch infrastructure. Political and funding realities complicate. Agencies hesitate funding one-off interceptors for targets of opportunity. Budget cycles are slow. Interstellar objects arrive unpredictably. Advocates argue for small-sat constellations as flexible alternatives. Keep multiple spacecraft fueled and ready in storage orbits. When target appears, launch the nearest spacecraft. Cost spreads over multiple potential missions, reducing risk of single target failure. Total constellation cost under $1 billion makes it affordable, compared to flagship missions costing multiple billions. Cinematic pitch imagines mission control during intercept. Engineers monitor telemetry as spacecraft closes on 3I-ATLAS. Cameras snap images showing nuclear structure for first time. Spectrometers record spectra in real time. Dust collectors extend, gathering particles. Then flyby ends, spacecraft continues, data streams back, teams analyze. Weeks later, results publish. Mystery solved. That's the dream. Reality involves risks, failures, compromises. But the engineering is feasible. Willpower and funding are bottlenecks, not physics. Part 15. Quantum Fundamental Physics. Surprise and Final Synthesis. ISS experiments in materials science reported unexpected behaviours under microgravity in 2025. Crystallization processes produce structures not predicted by ground-based models. Quantum fluids exhibited phase transitions at temperatures slightly different from theoretical calculations. Those shifts suggest refinements needed in many body quantum theory or unaccounted environmental factors. Dark matter direct detection experiments tightened constraints, ruling out parameter space, but not detecting signal yet. Each result, though not paradigm shifting alone, contributes to refining our understanding. The lesson is scientific eras of surprises, anomalies across fields, astronomy, gravitational waves, AI detection, mission design, quantum experiments, all point to a period where instrumental sensitivity exceeds theoretical anticipation. We detect things before we understand them. 3I-ATLAS fits this pattern. One more anomaly in an era rich with them. Synthesizing the leading outcomes for 3I-ATLAS, assign plausibility rankings subjectively and illustratively. 60% natural exotic chemistry. This remains the baseline. Supervolatiles, unusual composition, extreme but explainable. 30% data artifact. Instrument calibration errors, background subtraction issues, coincidental multi-instrument biases. Low probability but not negligible until full vetting completes. 10% engineered. This remains speculative, assigned low prior, updated slightly by anomalous observations but not enough to dominate posterior probability. These percentages are illustrative, not rigorous. Individual scientists would assign differently based on their priors and evidence weighting. Final, what-if vignettes offer payoffs. Scenario 1, confirmed exotic comet. Papers publish in March 2026 confirming supervolatile composition, identifying molecular emission lines, explaining brightness curve with fragmentation models. Textbooks update. Cometary chemistry expands to include carbon-rich interstellar visitors. 3I-ATLAS joins the catalogue as unusual but natural. Science progresses. Scenario 2. Confirmed engineered fragment. Spectroscopy reveals narrowband emissions inconsistent with known molecules. High-resolution imaging shows geometric structure, planar surfaces, symmetries. Independent teams replicate findings, papers publish, media explodes. Philosophical and scientific revolution ensues. SETI priorities shift. Funding pours into follow-up missions. Humanity grapples with confirmed evidence of extraterrestrial intelligence, even if indirect, even if ancient. Culture changes. Scenario 3. Artifact of instruments. Detailed calibration reviews find correlated errors in all 3 coronagraphs. Stray light plus vignetting plus background misestimation produced apparent blue colour and steep brightness curve. Real object was fainter, neutral colour, normal comet. Papers retract claims. Community learns lessons about coronagraph limits. 3I-ATLAS fades from public memory as cautionary tale. Science self-corrects. Call to action for the public and amateurs. Observe safely. Verify coordinates from trusted sources like Minor Planet Center or NASA JPL Horizons. Use apps to locate object in sky. Report observations to established networks, not social media first. Trust verified data channels. Be patient. Science takes time. Hype spreads fast but fades faster. Truth emerges slowly but lasts. Frame 3. I-ATLAS. As a mystery testing our instruments, models and patience. Either way, natural or artifact or engineered, the universe just made us rethink what we thought was normal. We're reminded that cosmos is larger, stranger, more surprising than models capture. Humility befits us, curiosity drives us, and the next interstellar visitor is already on its way, unseen, carrying its own secrets. We'll be ready. We'll observe, we'll analyse, we'll learn. That's what we do. That's what science is. The pursuit of truth through evidence, no matter where it leads, no matter how uncomfortable, no matter how wondrous. 3I-ATLAS gave us a gift, the gift of mystery. And mysteries are invitations to discover,